Hi everyone, this is the second lecture for week 5. Today you'll need your homework 5, your functional group sheet. Hopefully you were able to print that off so you can use that for easy access. You'll just need your periodic table, again just for reference, and today's learning objectives. Now I wanted to start by going over a review for you of the naming concepts that I talked about in lecture 5.1. I wasn't very satisfied with my quality of teaching, so I wanted to give you all a chance to go back through the material and present it in a clearer way, do some examples from your homework because I didn't do any of that, and then I totally forgot to go through some of the interesting types of those compounds that we see in nature or in real life. So we have a little bit of catching up to do from lecture 5.1, and I apologize for that. Okay, so I did not present for you a very clear step-by-step instructions for the nomenclature. So here is a more clear process that you should follow for naming those compounds. You're going to start by identifying the longest carbon chain and use the corresponding parent name. Remember, those are the meth, eth, bute, prop, etc. And then a couple of things to note: that you should always identify the longest carbon chain that has your functional group in it. So if your double bond is not part of the longest chain, you've done something wrong. And then you're going to want to use the appropriate suffix with that parent name, and that just depends on what functional group you have going on in whatever molecule it is you're looking at. Ane for single bonds. If you have one double bond, you should use ene. Triple bond should be ine. Okay. Step 2 is to number the carbons in the chain so that your substituents have the lowest numbers possible. We did several examples of this in the previous lecture. Step 3 is to name and number all of the substituents. Step 4 is to alphabetize those substituents. And just a side note here for number 4, prefixes di, tri, tetra, etc. Prefixes do not count in alphabetizing. So in other words, if you have dimethyl and ethyl, well, even though the D comes before E in the alphabet, we don't count those prefixes when you're looking at alphabetizing. So this one actually comes first, and then the dimethyl, because we're going by the name of the substituent, not by the name of its prefix. And then step 5 is to add numbers 4 and 1 together. So you're going to add all of your substituents to your parent plus suffix. And then just a couple of things to keep in mind. All numbers and words are separated by dashes, and all numbers are separated from each other by commas. We are going to be using all lowercase letters. Nothing should be capitalized, not even the first letter of the words, unless you're using them in a sentence. But for our purpose, these are not proper nouns, therefore they are not capitalized. Okay, now I want to do a couple of examples from your homework to give you a basis for when you start that homework. It's a 7-pager this time, but these compounds, when I draw them on my software that draws molecules, they come a little bit big. So you'll see that it's 7 pages, but it's not nearly as much work, I don't think, as the last solutions homework, for example. Okay, so let's start from the top. Let's identify the longest carbon chain. Well, the longest carbon chain in number 1 is not the linear carbon chain. It's the one that branches off down here. So we're going to count how many carbons there are here. 1, 2, 3, 4, 5, 6, 7. 7 is peptine. I know it's ane because I don't have any double bonds. Okay, then now step 2 is to number. And I want to number so that I have the lowest number for all of my substituents. If I start numbering here, I'll end up with 1, 2, 3, 4, and 6. But if I start numbering from the top here, I'll end up with 2 and 4. That's what we want to do. Okay. So now we need to name and number our substituents. Firstly, we have a 2-methyl. That's this thing. And then we have a 4-ethyl. That's step 3. Step 4 is to alphabetize those substituents. So I know that this one has to come first, and then the 2-methyl. Step 5 is to put everything together. 4-ethyl, 2-methyl, heptane. Notice that this is one word here. Make sure that you do that on your homework. I don't know how this got here. There. Oh, isn't that nifty? Okay, so here is number 3. So let us start with number 1. We have to identify the longest carbon chain. And I'm just going to use the linear carbon chain. That's 4, so we have butane. Then we have to number. Now I could either number this way, or we'll call it the red way, or I'll do the green way. The red way gives us a 3-methyl, while the green way gives us a 2-methyl. So we have to use the green way. So we have 2-methyl. And now because that's the only substituent I have, I can just go ahead and skip step 4 because I don't have to alphabetize anything. And so I can put it right at the end, or right next to my parent plus suffix. So this compound is called 2-methylbutane. Okay, now here is a tricky one. 1, 2, 3, 4, 5, 6, 7. Okay, so you have a couple of different ways of numbering this because the longest carbon chain is actually, you can go either this way or this way. Now, the compound is going to be symmetrical, so it doesn't matter which way you actually number. But I counted, I think, 7 carbons. 1, 2, 3, 4, 5, 6, 7. Yep. Okay, so we're going to have a heptane here. Now it's really important when you guys are using the naming, the 5 steps to name these compounds, that you do them in order. I know it's really tempting to start numbering and all of that stuff, but if you start naming the substituents and stuff, you'll really get off of track. So if you can start with your parent and your suffix, that's, you know, the meat and potatoes of the name. So you want to start there because then you can get a better feel for your compound. Okay, so I'm going to number here like this because that's a little bit easier to see when it's all horizontal and linear like. Okay, so now I've numbered. Now my third step is to name my substituents. So I do have 2 methyls on that 3 carbon. This is how you do that, 3, 3 dimethyl. So you have to write where those two methyl groups are, and then you also have to write di. And like I said on the last lecture, it is a little bit redundant that you have 2 numbers and the word di, or the prefix di, but that's just the convention. Okay, and then what is that thing on carbon 4? Well, that's a 3 carbon, 1, 2, 3 carbon substituent, and the name for 3 is propyl. So then we would have a 4-propyl. Okay, so we've done step 3. Step 4 is to alphabetize. And M comes before P in the alphabet. So our compound then is going to look like this. 3,3-dimethyl 4-propyl heptane. Now, as you can see, there are a lot of different parts to these molecules and to their names. There's a lot of places where you can go wrong. And if you can try to stay on track with those 5 steps and make sure that you're, like my mom used to say, keep your wits about you on each of the steps, don't mentally skip ahead to the next step until you have this thing down on paper. Because if you don't, it's really easy to get screwed up. So 3,3-dimethyl 4-propyl heptane. Okay, now there is a small group on the homework where you have to take a name and draw a compound. We didn't do any examples like this on the first lecture, so let's do one of these right now. Okay, so here we have 3,3-dimethyl octane. When you're drawing compounds from their names, I want you to do this in the backwards direction. So you want to draw the compounds the way you would write them. So always start with the parent carbon chain. So I'm going to start with that octane. 1, 2, 3, 4, 5, 6, 7, 8. And yes, I do only have 7 lines here. That's because, remember, each of those lines denotes a bond, not a carbon. Okay, so I've got the octane part done already. Now I need to put 2 methyl groups on carbon 3. Now, it totally does not matter if you start numbering from the right or from the left. I'm going to do that from the left. And that is carbon 3. 1, 2, 3. 2 methyl groups on there. And that's 3,3-dimethyl octane. Not so bad. I think we've got one more example. Yes. This is number 2, I think page 2 on your homework. Okay, again, start with the parent. Nonane is 9 carbons. And then we have 3 methyls. At 2, 4, and 5. It's very systematic, and if you follow the rules, you shouldn't go wrong. I really think naming and drawing compounds is really fun. But I'm a nerd. I don't expect you to think it's fun. Okay, here's one of those cycloalkanes that we talked about in the first lecture, but I wanted to do an example from your homework. Okay, so we're going to be doing the same process that we did for the linear alkanes, only we just add cyclo in front of the parent name is basically all we're doing. So we have to count the carbons in the ring, 1, 2, 3, 4, 5. So that means that we have a pentane. And remember, because it's a ring, we're going to want to write cyclo in front of that. So it's a cyclopentane. And now all of the steps are the same as what we had for the regular linear alkanes. And now I start with this number, this carbon as number 1 because this is an ethyl group. And I want to have my first alphabetical substituent group to have the lowest number. So that's why that's 1. And so we have a 1 ethyl, 2 methyl cyclopentane. All one word, all lowercase letters. 1 ethyl, 2 methyl cyclopentane. Okay, here we have an example of an alkene. Okay, so you're going to want to count how many you have. 1, 2, 3, 4, 5. Now we don't write ane anymore as our suffix because we have a double bond. Which suffix do you use? Ene. Okay, now the first thing is to number where that double bond comes in. So we have to do our numbering. We have to start from the left here so that this carbon here, the first one in the double bond, has the lowest number possible. This number is what describes where your double bond is located in the 5-carbon chain. You have to have that. And then you just have a 4-methyl. And remember, here you have a word and a number, so you have to put a dash there too. Every time you have a separation, you have to have that dash. 4-methyl-2-pentene. What kind of functional group does this compound have? Right, an alkyne. Now, what I want you to do is pause it, come back, and I'll give you the answer. If you're confused about where I got this name from, you should go back to the beginning of this video and watch it all over again. The more you can watch me do the examples, the easier it'll be. Okay, now, before we go on to new stuff, I just forgot to talk to you a little bit about why you should care about alkenes and alkynes. Alkanes are what we use, with all carbon-carbon single bonds. Alkanes are what we mostly use for fuels. Propane, butane, octane. All of those fuels, gases usually, come as alkanes. The reason why alkanes are used as fuels is because they're saturated. Remember what saturated means? It means you have the most number of hydrogens possible. In other words, you don't have any double bonds. I'm going to draw out for you the structural formula of propane. The most common fuel that you use for heating for home heating or for small grills or small engines. This is propane. Okay, so alkanes are used for fuel because they're saturated. When you burn something, it means that you're breaking bonds apart. And for every carbon-carbon and carbon-hydrogen bond that's broken, energy is released. So every time you break one of these bonds, energy is released. That's what you want. So in an engine, what happens is that you are basically burning your fuel, you're lighting it on fire in a reaction, and that in turn is the burning of your fuel is what produces enough energy to move your motor or do some work on your object. Without getting into the physics of engines any more than that, suffice it to say that breaking bonds means that energy is released. Therefore, the more bonds you have to break in your compound, the more energy that's released when it burns. So that's why octane rating is important. The higher the octane rating, basically, and this is in simplistic forms, the more bonds you have chemically in your fuel to break when it burns, therefore the more power your fuel can deliver. Okay, that's something interesting about alkanes. Alkenes occur in two ways. This is what's called the cis conformation. That word is conformation. This means that you have both of these carbons on the same side of the bond. are not on the same side of the bond. It looks like this, and this is called the trans conformation. Not confirmation like you have at church, conformation. How the bonds are set up in 3 dimensions. Now, in nature, there are no trans double bonds. There are no trans double bonds in nature. They don't exist in nature. It only exists in the cis conformation. And that's because the cis conformation is the one that has the lower state of energy. Remember I said the first lecture that all systems strive for states of lower energy? That's why. So when you have something, we'll be talking about this when we get to our biochemistry section in a few weeks. We have something called lipids, and lipids have long carbon chains at the end of their molecules. I guess I don't really want to draw that molecule for you right now because we'll talk about that in depth in a couple of weeks. But in the very long carbon chains at the end of the fatty acids and lipids, sometimes there are double bonds. If there are no double bonds, those lipids are called saturated, which means that they're basically alkanes. Saturated fats, are bad for you. Just like I said when we were talking about fuels, that every bond that gets broken releases energy. Well, when you're trying to digest a food, every time you have to break a bond, you have to use more energy. And if your body is not able to successfully break down anything that you ingest into your system, if it doesn't come out in your urine, in other words, if it's not water soluble, which fats are not, it gets stored in your body as fat. In lipids that are called so-called trans fats, that are, notorious in the news, trans fats actually have trans bonds in their fatty acid chains. So why are trans fats bad for you then? Well, if something doesn't exist in nature, trans double bonds don't exist in nature, it means that your body does not have any equipment to process trans bonds. Remember what I just said? If your body can't process it, it stores it as fat. So that's why trans fats are bad. Your body can't process them. They're not water soluble, so you can't pee it out. So your body can't do anything with it but store it right as fat. So if you eat those potato chips that have the trans fats in them, immediately when they come into your system, they just get stored right as fats. Now these are only the trans fats that I'm talking about. I'm not talking about good fats or anything like that. We'll talk about good fat and bad fat when we get to biochemistry. So that is why trans fats are bad. Another interesting alkene that's just interesting is this compound here, or what is this is a precursor to what is known as PVC. PVC is polyvinyl chloride. This is the molecule PV. This is one of the repeating patterns of polyvinyl chloride. This is how it starts out. So that's how you can make PVC, is from this alkene. Just something interesting. Just a little tidbit. And then I just wanted to share with you a couple of different interesting alkynes, just so that you have some sort of real life connection that you can make between these weird compounds that you have to learn how to name. Okay, so the first interesting alkyne is acetylene. Acetylene is its common name. That's what we refer, it's not its systematic name. This is what we refer to it in the common lexicon. This is what acetylene looks like, and acetylene is used most commonly as a fuel for welding torches. It has a carbon-carbon triple bond. Another interesting alkyne, I have to use my paper here, my best attempt at pronouncing that, is an oral contraceptive. And what it does is it has two different synthetic hormones. It has an estrogen, a synthetic estrogen. I'm trying to hurry so that I don't have a huge video to upload, and you can tell because my spelling has just become horrible. So we have a synthetic estrogen in this compound and a synthetic progesterone. And what the synthetic estrogen does, it fools the body into thinking it's pregnant. What doesn't your body do when it's pregnant? Well, for you guys, sorry. Fools the body into thinking it's pregnant. If your body is pregnant, it doesn't produce eggs. So you will have no egg release. You won't be producing any eggs. There's nothing to fertilize. The progesterone part stimulates the production of a thicker membrane around the cervix. And when you have a thicker membrane around the cervix, it means that it's very, very difficult for the sperm to even the very small sperm molecules, is very difficult for them to pass through that thicker membrane around the cervix, which means that while you're not producing eggs, no sperm will be able to enter the fallopian tube to fertilize the egg. And this compound, as you can see by the Y in the name, is an alkyne. It's interesting when you talk about it in terms of drugs, isn't it? Okay, in our next part we'll be talking about some new material.